All right, guys, next unit here, we're going to be going over dimensioning and tolerancing. Fun stuff. So, goals for this is to differentiate between linear and angular dimensioning and tolerancing, what the significance is of tolerances and the terms associated with fit up of parts. And then compare and contrast conventional and baseline dimensioning. Those are like the two main categories of dimensioning, and then how to interpret radius and arc dimensions. So some basic stuff, but there is quite a bit of slides on this one. So dimensioning. Exact dimensioning of the parts is necessary, so one part can be substituted for another. Typically, dimensions on a print specify the length, width, thickness, and location of objects on a part. All right. Uh, the U.S. customary method, that's just fractions, feet, inches versus like the metric system. That's typically what we use, but metric system you'll see pretty frequently as well on prints. That's really just up to who's designing the part. So first method is conventional dimensioning. This gives dimensions for the overall length, width, and thickness of the part, and then distance between objects, but it does not give the exact location of every part. Okay, so this is a way to kind of clean up the print a little bit without having too many dimensions on it, because you see some advanced prints and it's just covered, and it makes it a little more difficult to kind of see. So sometimes they'll do conventional dimensioning, which means you'll have to do a little bit of math to figure out the location of some parts. All right, so there's an increased risk because of this for measurements. Okay, so an example, right? We know this hole is 2 inches from the edge, and then this hole is 2 1/4 from that hole, and then this hole is 4 1/2 from this hole, and then this hole is 2 1/4 from this hole. All right, so the most accurate measurement, because you're coming off the edge of the part, is going to be this first hole, but then you're going off that hole to this one, off that hole to that one. So just imagine yourself out in the shop actually doing it that way. It's going to be a little difficult, a little more tedious getting an exact center point perfectly 2 1/4 from that center hole to that one, from that center hole to that one, versus if you just measured and had the dimensions of what is the measurement from the edge of the part to this hole, it's 2 inches. Well, what's the measurement of the part from this edge to this hole, okay, and so on and so forth. And then also it'll leave out certain dimensions, and you'll just have to figure out the math on that. Okay, so it's not like an impossible thing. It's just it takes a little more effort, but it does clean up the part as far as the drawing goes. And then you have baseline dimension. So this has all the dimensions referenced. Okay, so the advantage to this is obviously less risk of an error, but it increases the clutter of the print, because now you're going to have from this hole, boom, 2 inches, from this edge, boom, 4 1/4 from this edge, 8 3/4 from this edge, 11. All right, so you're going to have an increase in the amount of dimensions in it, but it's going to be a little more accurate as far as the locations go. All right, so that's the difference between baseline and conventional. So getting into types of dimensions, we got linear dimensions. All right, this is straight lines. This is again typically like the length, width, thickness of the part and where holes are located. This is used to size parts and locate objects of a part. Okay. U.S. customary, again, that's like inches and feet is typically used, but the metric units may be used. Again, that just kind of depends on who's designing the thing. Fractions of an inch can be expressed as either common fractions or decimals. Okay, so again, just a preference, sometimes both. Typically though, it's going to be one or the other. So if the part has fractional common fractions on it, typically that's the style they're sticking with. Or decimals. It's usually one or the other. Okay, angular dimensions. So you got a couple examples right there. So this is used with welding prints to specify both alignments of parts and to indicate the amount of beveling or chamfering with joint design. So think about you structural guys that are taking this class. When you're prepping all your pieces, there's going to be a few examples that you guys should be able to relate to. Everybody should be able to relate to a skew joint though, right? So think of this as just a T-joint you're getting ready to weld. Typically, we say T-joint and you automatically think, boom, 90 degrees, right? Well, sometimes parts aren't exactly at 90s, or maybe you tacked your part together and it kind of leaned over a little bit. That would now be considered a skew joint. All right, a skew joint is simply fit up at an angle other than what is considered typical for that joint. All right. Angular, continued. So also used to indicate the amount of beveling or chamfering. Okay, so the primary difference between chamfers and bevels, the process to make them is going to be the same. The only difference really is on a bevel, that's typically where you're going to weld, and a chamfer is typically on an edge, like an alternative to doing a radiused edge. Okay, so that's really the only difference between the term bevel and chamfer, but it's the process is the same thing. Okay, so again, chamfer typically found on the exposed edge, bevels typically associated with the welded joints. Okay, like this butt joint right here. All right, so this is a little weird one. I've never seen this on a print out in the industry, but this is typically done for more advanced, really precise uh, um, details of a part. So the most common way to indicate angular dimensions is to use extension lines with a curved dimension line and the angle of the dimension written with the extension lines. All right, we'll show you that in the next slide. Size of the angle is typically expressed as degrees, sometimes expressed as minutes. All right, and this is just a way to break down 4/4, all right? So 15 minutes, quarter, 30, half, 45, 3/4, 60 would be a whole, okay? As opposed to thinking of 365 degrees and what's half of 290, or, it gets a little caught in the weeds sometimes. Are we going negative or are we going positive? So sometimes they'll just use it as a reference, minutes, okay? So 15 minutes, that's quarter of 1 degree, all right? And this is when you're getting down to like the point, right? Like 29.8 degrees. Okay, sometimes they'll reference it as minutes instead of 1/4, half, 3/4. So the bevel angle and depth of beveling should be identified in the welding symbol. You would subtract the depth of the bevel from the plate or pipe wall thickness to determine the thickness of the landing. Okay, so coming back to you structural guys, when you're prepping your material for your qualification plate, if you were looking at a WPS, and hopefully you guys are going over that in your structural class as well, to find the bevel angle and the depth of the bevel, right, the depth of the bevel, 5/16, you would subtract the depth of the bevel from the plate thickness. So we want 5/16 bevel depth, we have a 3/8 plate, that would give us the landing, okay? When both plates of a butt joint are beveled, welding symbols should identify the bevel to be done as included angle. All right, the included angle simply means both angles, right? This is not a 60-degree angle and a 60-degree angle. This is a 30-degree angle, a 30-degree angle, and the included angle is 60. So again, you structural guys, I'm sure a lot of you guys are doing like your 70/18 3G. So you're probably doing like a 22.5 bevel, a 22.5 bevel, and your included angle would be that 45-degree V opening. All right, so that's what the included angle is. It is the sum of degrees of beveling on both plates. So beveling on each plate is half the included angle. When we're talking about pipe, this can be open root, or a space can be fit up at root faces, right? Your root face, that's that landing right there. The print or the code will specify what the root opening should be. Okay, so I think for a lot of the certs you guys are going to be dealing with, it's like a 1/16 or 3/16 or quarter inch, depending on what process you're doing. And that's just the space between the two landings. That's what the root opening is. So if the directions for depth of beveling are not given, okay, so they're not telling you what the depth of the bevel is, that means there should be no landing. Okay, we call that a feathered edge, where it just comes to a point. There's no flat spot, there's no root landing. All right, so if they're not telling you what the depth of the bevel is, it should be whoop, a straight line all the way through, and that's called a feathered edge, where it comes to a sharp point, sometimes also known as a knife edge. Okay, So that's a feathered edge present instead of the root face. Typically larger root opening, and this is where you start using backing bars. Okay. Okay, so talking about rod, all right, that's stock, not tubing or pipe. That's solid rod. All right, so square, rectangular, and round rod can be beveled or chamfered on both sides. That's going to be denoted on the welding symbol. Okay, not in the drawing, not on the print, but on the welding symbol specifically, if it's going to have a chamfer or a bevel on it. Okay, radius. All right. So dimensions specifying the size of an arc, that's really all a radius is. Um, we use radius. Okay, so when you look at something, if you see that R next to a dimension, that's telling you that's the radius of the part, as opposed to the diameter. Okay, so linear measurements that create a center point right here, 1 inch from the side, 1 inch from the bottom, that's going to give you the center point of the radius. And if you have equal dimension lines, right, 1 inch, 1 inch, the radius is going to be that size too. So 1 inch, 1 inch, it's going to give you a 1 inch radius. Okay. This is preceded by the letter R. Again, for diameter, we have a different symbol. Both inside and outside radius may be given. Okay. Most commonly, though, you're going to see it on the inside because you're typically going off of a center point, kind of like a hole or a circle. Sometimes they are uneven, though, right? So we've got the center point off the part. So you would have to figure out when you're fabricating this part, a creative way to get this piece locked down, make your dimension lines 1 3/16 off the edge, 1/4 inch out of the edge, make your center point off the part, and then get your compass, boom, and get that 1 1/4 inch radius. All right, so sometimes you have a part comes to 90-degree edges. Sometimes you want to radius those. Okay, so that's another use for having a radius. Um, in this example, right, we can see we want a 1/4 inch radius. It says typical. All right, that's what that stands for. When you see that typical, that's just telling you that both are going to be the exact same. So we've got the radius being said right here, and then we have the dimension lines for the center point right here. But it's going to yield the same radius. Okay, so that way we don't have to have this 1/4 inch, and the radius, and then 1/4 inch, and the radius. Kind of help. This is one of the ways you can kind of tidy up and have less information on a print. So when you see that typical, any other corner like this will also have the same radius. Okay, and again, we're going 1/4 inch, which means we're going to have a 1/4 inch radius. Okay, so we can also use this on the end of round rod. Again, not tubing, this is round stock. Will be spherical since the rod is round. So imagine you just needed, instead of having a flat cut, they wanted a radius on it for some reason, whatever reason. Typically, this is almost always half the diameter of the rod. Okay, that's what yields the most symmetrical shape, right? So this is a nice half circle basically. So we have a 1/2 inch diameter round rod. We're going to go 1/4 inch, center point, and that's going to give you a nice symmetrical radius. All right, if we had 1/2 inch round stock and we did 3/8, it might come more to a point, or if we went less, it might come more like just a small stub. All right, so when you're cutting that in half for a radius, that's going to give you the most symmetrical shape. So hole dimensioning, typically placed on print with a leader line. The arrow points to the object line representing the hole in the part. The hole size will be a note written at the end of a horizontal line or of the leader line. Okay, and this is the diameter symbol. All right, a little confusing because for radius we have an R, for diameter you got an O with a strike. Okay, so but this is the symbol for a diameter. Okay, symbol indicates dimension specified is the diameter of the hole. So a diameter and radius, both used for circles. Diameter is just twice the radius. So if you ever get confused, just remember that a radius is half of what a diameter is. A radius is being measured from the center point to one end. A diameter is being measured from edge to edge of a circle. Okay. This can be either drilled or punched with a hydraulic punch. When we're talking about holes, you can also, if it's denoted in the notes, sometimes it'll be required to do like an oxyfuel cut, a plasma cut, machine. It just depends. Holes not drilled or punched completely through is called a blind hole. All right. So on the print, you'll see maybe a diameter for a hole, and then it'll say through. That means that it must go all the way through that part, completely through that part. Blind holes do not pass completely through the part. Okay, so 1/2 inch diameter. All right. So another way to measure this would be if you had a dimension line coming off that edge, a dimension line coming off that edge with a 1/2 inch dimension on there. Okay, but for again saving space when we're doing circles, typically it's just a leader line off of it, 1/2 inch diameter. Okay, and then 1/2 inch through. So that's telling me this needs to go all the way through that part. Okay, and then again, typical. So right here, you've got two different sized holes. All right, this is a through hole, and then this is a 1/2 inch through hole, and then this is a 3-inch drilled 1/4 inch DP. Okay, so they're threading this. And then you need to denote that because they're two different sizes. But over here, we've got 1/4 inch typical. So instead of having a 1/4 inch diameter on each one of these 4 holes, you just boom, 1/4 inch typical. The guy making the part knows that all 4 of these holes needs to be 1/4 inch diameter. All right, so typical is just, again, another way to kind of clean up repetitive features. And I kind of mentioned this already, so holes can also be done flame cutting or plasma cutting. So you will see an OFC or a PAC, the acronym. You guys should start memorizing these. There's a unit later on this semester that you need to know all the acronyms for all the different welding and cutting processes. And this includes like if you know what GMAW-G is or GMAW-P is, okay? Things like that. So start memorizing these acronyms. Okay, countersinking. So additional finishing processes include things like countersinking or counter boring. A countersink, this is like a chamfered inside a hole so that the head of like a flat bolt can sit flush with this edge. Okay, maybe this is a flooring part, or maybe another part is moving past this. Think about like the shear when the blade's coming down. There are bolts that hold the blade in there, and they are countersunk so that the bolt heads aren't sticking out. All right, and on the print, that's going to be denoted as CSK right there. So you have a 1/4 inch drill through, so that's a 1/4 inch through hole, and then a 3/8 countersink. Boom. And then counter boring. Basically the same thing, we're just not at a bevel. All right. So you'll see a lot of stuff like this on like heavy equipment. Because they want to protect the heads of those bolts so that when they go to service the machines, they're not completely ruined from abrasive, from rocks, from dirt, things like that, rubbing up against them. So you'll counter bore so that when that bolt goes all the way through, it's protected. It's not sticking out. Okay, but just another way to kind of sink in a fastener. Okay, and these are going to be denoted with C bore, right? 1/4 inch punch. So that's telling me I need a 1/4 inch hole punched using a press, and then a 1/2 inch counter bore. Boom. And then spot facing, this is similar to counter boring, except the depth will not be specified. Okay, so this is meant for when you have a rough surface, like an uneven surface. Okay, spot facing, when you're using fasteners, bolts and nuts, you want the bottom face of that bolt to be flat. You don't want it on an uneven surface. You want it as flat as possible. That's going to give you the most tensile strength. So if you have a really rough surface, sometimes you'll spot face it, which just means you're trying to get a flat spot in there so that the bolt will sit flush, okay, on the surface to maximize that tensile strength when you start sandwiching this to another part over here. All right, and that's going to be denoted as SF. Okay, so we have a 3/8 diameter hole drilled, and then a 5/8 spot face so that that bolt head has something flat to rest on. Okay, so we're getting into tolerances now. So we have base size dimension, dimensions stated for a part on a drawing. Okay, that's just the what that part is supposed to be dimensioned as. All right, and if you for the fabrication guys, I'm sure you'll hear Camacho talk about tolerances on and off when you're doing some of your 3A projects. We always have like a plus or minus tolerance on projects, right? If you're squaring up a trailer, you want to like plus or minus a 16th. Okay, so that's no more than an 1/8 inch off total. Okay, and so on prints, these are going to be denoted as a plus or a minus. Okay, so tolerances, those are going to be denoted by the engineers or the code, but they will be on the print. And then if you break the allowance, all right, no longer will that work be acceptable and you'll have to go rework it. Okay, so tolerances are very important to pay attention to. Prints using common fractions will state tolerances in common fractions. Prints using decimal fractions will state tolerances in decimal fractions. Okay, so to eliminate confusion, one or the other. All right, and then angular tolerances are typically stated in degrees. More precise parts could have it done in those minutes that we mentioned earlier, but typically degrees are degrees. All parts within stated range are referred to as actual size. So as long as you're in that range, it's considered actual size. That means regardless of the scale, I have an 8-inch part. As long as you're in that tolerance, even if it's a 30-second off, if you're within the tolerance, it's considered the actual size of the part. Okay, now getting into scale. For the most part, welding prints are reduced scale. That's the most common, right? Typically what you're looking at on a print is a smaller version of the actual part. So this is like a 1:2 ratio, 1:4 ratio, 1:8. So half scale, that means 1/2 inch on print is actually 1 inch on part. Full scale, also known as like a 1:1 ratio, means 1 inch on print is 1 inch on the part. And then in large scale is the opposite. This means the print is larger than the actual part. So this is like you zooming in on a small part. Okay, this is used to detail small parts. And then the numbers just reverse, right? Now you're going 2:1. 2 inches on print is only 1 inch on part. And typically in programs, you'll see it labeled not as 1/2 inch, 1/4 inch, or 1/8 inch, or half scale, quarter scale, 8 scale. A lot of times it'll be like a 1:1, 2:1, or a 1:2. Okay, because sometimes you're going back from uh, our system, inches and fraction or inches and feet to metric. Okay, so kind of like going from metric and the common on our side, the inches, to engineering terms. All right, so engineering measurements. So that's kind of what that 1:1 ratio or 2:1 ratio or 1:2 ratio kind of denotes in those programs. All right. So good information on this one. Make sure you're paying attention to the discussions, and we will see you on the next unit.